In this video, we're going to talk about transformations of random variables and also moment generating functions. So for transformations, suppose we know the distribution of some random variable x, but we're actually interested in y, which is some function of the random variable x. Can you think of some examples that might be relevant to this case? One might be if x is the price of a stock and y is the payoff of an option. Then we'd really be interested in y, the value of the payoff, which is a function of the stock price. So we can always find information about the distribution of y from the distribution of x, either the PDF or the CDF, in a couple of different ways. The first way is called the CDF technique. Step 1 is to find the range or the support of the random variable y. Step 2, we want to write the CDF of y in terms of the CDF of x. And the exact way that that goes will depend on what that relationship is, what that function h is. And then finally, we want to use what we know about x to evaluate the CDF of y. And then, of course, we can differentiate if we want to get the PDF. And it's important to note, we could do these two parts of step 3, plugging in the CDF of x and differentiating to get the PDF, in either order. We could either plug in first and then differentiate, or we could differentiate first and then plug in. And some situations might be easier one way or the other. So let's look at an example of using the CDF technique. Suppose we have the random variable x with a probability density function little f of x equals 3x squared for x between 0 and 1. And we're going to let y equal 1 over x. And we want to find the PDF of this function y. So step 1, we want to find the range of y. And it's going to be 1 to infinity. Now think about why that is the case. Give that a bit of thought. Here, we know that x goes between 0 and 1, and y is 1 over x. So we can kind of think about all the possible values that y can take on. If x is very small, very close to 0, then y will be very large, up to infinity. There's no maximum. If x is near its maximum value, near 1, then y will be 1 over 1. So any value of x between 0 and 1 will result in a value of y between 1 and infinity. Okay, step 2, we want to write the CDF of y. So that's just subbing in 1 over x less than or equal to y. And that's going to be some relationship between x and 1 over y. We're taking the reciprocal of both sides inside that probability. But remember, when we take a reciprocal, we have to switch the direction of the inequality. So that's just equal to 1 minus the CDF of x evaluated at 1 over y. Okay, but we know that the CDF of x we could get by integrating from 0 up to x of the PDF at u du. And that's going to give us 3u cubed over 3 evaluated at 0 and x, which is x cubed. So now we can do step 3. We can sub in. We'll look at 1 minus 1 over y cubed, just subbing in 1 over y into the CDF of x. And then we can differentiate to get our PDF by taking negative and then minus 3 times 1 over y to the 4, which is 3 over y to the 4 for all values of y greater than 1. So in this particular case, the transformation that we did here, y equals 1 over x, is a one-to-one transformation. And later on in this video, we'll see a faster way to deal with one-to-one transformations of random variables. But for now, let's look at another example. Now suppose that we have x being a uniform random variable from -1 to 1, and y is going to be x squared. Again, we want to find the distribution of y, in this case, the CDF. But I want you to note, in this case, we don't have a one-to-one transformation. Y equals x squared is not one-to-one when x can be between -1 and 1. Because we could have two values of x that map to the same value of y, right? Like -1 and 1 both map to 1. 0.5 and -0.5 both map to positive 0.25. So it's not a one-to-one transformation, but we can still use the technique. So we'll look at the range, and that's going to be from 0 to 1. Now again, see if you can justify this to yourself before moving on. So we have here x between -1 and 1, and if we think of all the possible values x squared can take, the minimum is actually 0. The maximum is 1. So -1 and 1 will both map to 1. Anything between -1 and 0 that's negative will map to a positive value between 0 and 1, and then obviously anything between 0 and positive 1, when we square it, will map to something between 0 and 1. So there's not always a magical way to find the range. A good thing to think about is looking at the endpoints, but that doesn't always work. In this case, we have to consider what all the possible values of x can map to under this transformation y equals x squared. All right, for step 2, we're going to write the CDF of y as the probability y squared is less than or equal to x, and we'll take the square root of both sides, but remember, that means the absolute value of x is less than or equal to the square root of y. So that just means that x is between negative the square root of y and positive the square root of y, which we can write in terms of the CDF as big F of root y minus big F of negative root y. What is the CDF of a uniform random variable? Well, it's x minus a over b minus a, and subbing in those values of a and b, we get x plus 1 over 2, and then we can do step 3, we can sub in what we know. So we'll have square root of y plus 1 over 2 minus negative the square root of y plus 1 over 2, and that just gives us 2 root y over 2, which is root y, for y between 0 and 1. Now I want to talk about the second technique, which is known as the PDF technique. This can only be used if we have a one-to-one transformation. In other words, like an invertible transformation. So if y is h of x, that's an invertible function, we'll just let g of y be the inverse of that function, such that essentially x is equal to g of y. And then this PDF technique is super simple. The first step is the same, we just find the range of y using the same rules as before. And the second step, we can just straight up write down a formula for the PDF of y in terms of the PDF of x. We need the PDF of x evaluated at g of y, so that's evaluated at that inverse, multiplied by the absolute value of the derivative of that inverse. So it's just a formula, and actually, think about how you might be able to prove it. I might actually ask you to do this on an assignment, but I'll give you a hint now. So if we know that h of x is an invertible function, that means it's either strictly increasing or strictly decreasing. So you can consider those two cases separately. And in each one of them, essentially you can write the CDF of y in terms of the CDF of x and then differentiate. But you need to use the chain rule when you differentiate. And notice that in one of the cases, g of y, that inverse is going to be an increasing function, and in one of them it's going to be a decreasing function. So that's why we end up with that absolute value on the derivative, because the PDF in the end has to be positive. So give that proof a try if you like. All right, let's look at an example. Same as that first example we did. We had x with PDF, little f of x is 3x squared for x between 0 and 1, and y was 1 over x. So again, we know what the range is, 1 to infinity, and since this is a one-to-one transformation with the inverse just equal to x equals 1 over y, we can just plug in the formula and use the PDF technique. We'll get little f of y is little f of x evaluated at the inverse, so in other words, evaluated at 1 over y, and then multiplied by the derivative of 1 over y. Well, the derivative of 1 over y is negative 1 over y squared. So we're going to take the absolute value of that, and that'll get us 3 evaluated at 1 over y squared times 1 over y squared, which is 3 over y to the 4th, which, if you double check, is exactly the same as what we had before. So obviously this is much faster than using the CDF technique, but just be careful. It's only possible to use it when we have a one-to-one or an invertible transformation between x and y. All right, lastly, I want to talk about moment generating functions. This is a topic that a few people said they were a little bit confused with from Stat 230. We're not going to be using them a lot in this course, but they will come up occasionally. So I wanted to give you a bit of review on those. So we define the moment generating function of a random variable x, or MGF for short, as mx of t, and it's just the expected value of e to the power of tx. So depending on whether this is a discrete or a continuous random variable, it's either the sum of e to the tx px or the integral of e to the tx f of x dx. So always integrated or summed over all values of x. And there's a few properties that the moment generating function has that might be useful. First of all, fairly obviously, mx of 0 is equal to 1. If you imagine plugging in t equals 0, we get e of e to the 0x, which is just 1. Also, we can think about mx of t as being unique to the distribution of x. So if two random variables have the same moment generating function, they actually have the same distribution. You can use the MGF to uniquely determine the distribution of the random variable. So that can be handy for proving things. If you can show that the MGF of a variable is something that you recognize, then x has that distribution. And finally, the reason that the moment generating function has its name is that derivatives of mx of t give us the moments of x when we plug in t equals 0. And moments, again, by definition, are just the expected value of various powers of x. So let's see how that works. Imagine we have mx of t. It's the expected value of e to the tx. But we could write that as the expected value of 1 plus tx over 1 factorial, tx squared over 2 factorial, tx cubed over 3 factorial, etc. That's just the series expansion of e to the tx. What we can do then is use the linearity of expectation. So pull everything that doesn't involve x outside here, and we'll get this sum as follows. We'll have 1 plus t e of x plus t squared over 2 e of x squared plus t cubed over 6 e of x cubed, etc., going off to infinity. And now I want to think about what happens if we take a derivative of this function with respect to t. So the first term will be 0, the second term will be e of x, and all of the other terms after that will have some power or more of t in them, off to infinity. So if we set t equal to 0, mx prime of 0 is just e of x. Because every term after the second one there is going to be equal to 0 when we set t equal to 0. So that's neat. If we take a single derivative of our moment generating function and then plug in t equals 0, we get the first moment, or the mean, of the random variable. Similarly, we can do the same thing for the variance. We can take the second derivative, and then obviously those first two terms are going to be 0. We'll be left with e of x squared plus a bunch of things that have t in it. And then if we set t equal to 0, we'll get e of x squared. So that can give us the variance. In general, the rth derivative of the MGF, evaluated at t equals 0, is going to give us e of x to the r, which is the rth moment of the random variable x. So let's look at an example. Imagine we have x as a Poisson random variable with parameter mu. I want to find the moment generating function, and then we can use it to find other things about it. So mx of t, this is a discrete random variable, so we'll have the sum of over all possible values of x of e to the tx times that probability function p of x. Well, subbing in for a Poisson random variable, that's e to the negative mu, mu to the x over x factorial. So to evaluate this sum, first we'll take out e to the negative mu, and then we'll combine those together, and we'll have the sum as x goes from 0 to infinity of mu e to the t, all to the power of x, over x factorial. Now here's where you might want to remember a little summation result. If we have the sum as x goes from 0 to infinity of a to the x over x factorial, that's just e to the a. That's just the definition, or one of the series expansions of the exponential. So what we have in our sum here, the a is being played by mu e to the t. So that whole sum is just equal to e to the power of mu e to the t. And then we can factor out. So we'll have our moment generating function e to the mu times e to the t minus 1. All right, now we can actually use this moment generating function to find the mean of the Poisson random variable. We'll take one derivative of this function, and we will need to use the chain rule. So we'll have e to the mu e to the t minus 1 times mu e to the t, which is the derivative of the top with respect to t. So that gives us our first derivative. And now we can set t equal to 0 to get our mean. So we'll have e to the mu e to the 0 minus 1. Well, that just gives us 1. And then mu, and then e to the 0, which is also 1. So that gives us mu, as we expected. We could actually do the same thing for the variance, right? If you take the second derivative, and if you're going to do that, notice that you will need the product rule, because we have a function of t times another function of t, and then you can do that to show that the variance of x is equal to mu. So I would suggest giving that a try, especially if you're a little bit not sure about how moment generating functions work. And you can also try it for other distributions. You could try it for the binomial. It gives us a pretty nice result there. The geometric's pretty nice. You could even try it for some of the continuous distributions that we've talked about. The exponential has a nice closed form for the moment generating function. So for all of these, you can try finding the moment generating function and then using it to find the mean or variance of various other distributions. All right, that is everything for this video and everything for this week. In the tutorial on Wednesday, we'll have lots of time to practice some of these techniques, and I will see you then.